Hello and good afternoon, everyone. I hope you are all doing great. This is our seventh week, and this is the vector spaces introduction. I thought it's really very nice to record this session for you and to be with you. I will send the PDF for this lecture as fast as possible on WhatsApp. And of course, as you know, all of our course notes and references, you will find them on Moodle. So you should be in a very good shape. And of course, the recorded lecture, we can find it easily on the YouTube as usual. I will start today about a new topic, which is introduction to vector spaces. This is really a very important topic in the concept, in the meaning, and in the application. We will start by some uh, 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 some references and with some definitions and symbols that will be used through this chapter. The concept is very nice. It covers the either the vectors, the matrices, the objects, the operations on matrices, the polynomials, as we will see through various problems. Okay, let's get a summary for this chapter. First of all, the mass logic symbols with meaning that we may face during our journey through this chapter. Okay, the upper arrow, which means and. So if you see this symbol, it means x and y. The dot stand for x and y also. The plus is or. So if you see x plus y, it's x or y. The and notation, it symbolizes the and meaning, and that it means both of them. The vertical line, it's either x or y. It's either x or y. Or usually, like it's an arrow with a head look downward. Those two definitions are really very important. This is x and y. This is x or y. This is really very important. You have to put in mind in plenty of a heading of questions, definitions, and statement through all the chapters. So it's really very important to keep in mind. Okay. Also, this double arrow, it represents equivalent. This is implied to, that belongs to, that doesn't belong to, or not an element of, and you will have here examples on all of this. Also, this symbol, it is for every or for all. So I can say 2n is even for every n belongs to in capital, where n is a set of natural numbers. Also equivalent or if and only if, which represent this will happen if and only if this condition is satisfied. This symbol is doesn't exist. On the other hand, there exists. And of course, this is since or because. Those are some of the symbols that we usually use during our statements or writing expressions or questions through this chapter. So it's really very important to put them in mind. Once more, the reversed A with a dash in it, it means for every. The arrow with the head up, it means and. The arrow with the head down, it means or. And we will read all these statements in plenty of our slides in the coming on the coming slides, and not just only in this session, on the coming sessions too. So you will be familiar with. Okay, definition. What's a vector? A vector in the plan, a vector x in the plan, is represented geometrically by a directed line segment whose initial point is the origin and whose terminal point is at x1 and x2. We call it, in most cases, a position vector. So if x is a vector or a position vector, it will be the values of this point. But actually, it is the vector connecting 0 and 0 and that point. This is for the definition in the vectors. The bullet at the end of the arrow is the terminal point x1 and x2. The vector is represented, as you can see, as I can say x is equal to x1 and x2, or v is equal to x1 and x2. And this is really very important. Okay, some famous properties of vectors that we will need also in this session. We do this because other information is superfluous on this information. Two vectors u, which is components u1 and u2, and the v with components v1 and v2 are equal if and only if u1 is equal to v1 and u2 is equal to v2. So two vectors to be equal to each other, the first component should equal to each other and the second component should equal to each other. You should put this into mind. If I have just two vectors, u and v, and we would like to add them together, so the components of the resultant vector will be the sum of the first components and the sum of the second component. Just let me a second, I will get my laser pointer. Okay, once more. So a sum of two vectors u and v is simply adding u1 to v1, that's for the first component, then u2 plus v2 for the second component. The multiplication by scalar also goes really very smoothly with the multiplication of and the definition of vectors. If you multiply a constant by a vector, both its components will be multiplied by this value. So if I have v with two components v1 and v2, and if I multiply it by a constant number, the first component will be multiplied by c and the second component will be also multiplied by c, as you can see. So for a scalar c and the vector v, v1 and v2, defined by zv, it's c v1 and c v2. Okay, the discussion of vectors in a plan can now be extended to a discussion of vectors in n spaces. We saw previously the simplest form of a vector in two dimension, where you have just only two components, u1 and u2, or v1 and v2. We saw the addition and we saw the multiplication by scalar. This definition can be generalized either for R3, for R4, or for Rn, which means a vector in n space. This is why they call it n spaces or vector spaces. It is represented by an ordered n tuples, x1, x2, blah, 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 xn, which means it contains xn coordinates. So if I'm talking in R2, I will have two coordinates. If I'm talking in R3, I will have three components or three coordinates. If I'm talking R4, I will have four coordinates, and so on. The set of all ordered n tuples is called the n space and is denoted by I by R to the power of n. So once more, for R1 is the space or the first space, it's set of all real numbers. It's like the real x, so it has a zero in the middle, positive to the left, positive to the right, and negative to the left. If I have R2, R2 represent the two dimension space which have two tuples or two coordinates, x1 and x2. The both of them belongs to the set of real numbers. If I'm talking about R3, we means we are in the 3 space, which is a set of all ordered triples, x1, x2, and x3 of real numbers. So R3, we are talking about the 3-dimension space where we have x, y, and z, as you can see. R4 stands for the 4 spaces. So you know that we will have 4 coordinates, x1, x2, x3, and x4. And each one of them belongs to the set of real numbers, and so on. This is one of the simplest definitions about vectors. Let's check this group of vectors. If you remark for u, it belongs to R4. Why R4? Because it contains 4 components. This is the first component, the second component, the third component, and the fourth component. In a similar manner, V also contains four components, first, second, third, and fourth. Okay, let's find W such that this equation is correct, which means 2U plus V minus 3W equal to 0. If I want to solve this equation for the value of W, it's going to be really very simple. All I have to do is to move 3W from the left-hand side to the right-hand side. So I will have 2U, okay, so I will have, as I told you, 2U plus V on a side and the 3W on the other side. And then I will divide both sides on 3. So W would equal to 2/3 of U plus 1/3 of V, which is really very simple. I will multiply the value of 2 over 3 in the four components of the first vector, and then I will add 1 over 3 times the four components of V, and then I will have this shape of this vector, which is 1/3 for the first component, negative 8 over 3 for the second, negative 16 over 3 for the third component, and just only 3 for the fourth component. This is really very nice introduction, gathered the definition of a vector, how vectors are equal to each other, how to do the addition of vectors, how to get a multiplication of vectors together. Let's look to the vector space. What's a vector space? This definition is legendary and it's really very important. A real vector space is non-empty set. Put a line under this statement. A real vector space V is a non-empty set. So it can't be an empty set. It's a set at least contain the zero or the null vector from any dimension. We called vector space or are called vectors in which there are two defined operations, which is addition and the multiplication by scalar. So for every u and v and w belongs to the vector space V, for every a and b belongs to R, we will have the following properties. Once more, what's a vector space? A vector space is a collection of vectors or a collection of objects share some condition or some property, and under this property, the following should exist. Number one, closure under addition, as you will see. Number two, closure under scalar multiplication. In order to make this very obvious for you, let's say for our vector space, I will consider that it has u, v, and w. Those are three vectors belongs to v. And also, I will consider a and b, which belongs to r. Those are two constants belongs to the set of real numbers. So they could be anything. 0, 1, 2, 4, 5, negative 1, negative 2, negative 3. Any numbers belongs to the set R. For those vectors or the collection of these vectors to be called a vector space, the following should be found. First of all, addition closure. So each two vectors belongs to this vector space. Their addition should be, or the value of their addition should be a new vector belongs to this set. This is number one. Also proves additive associability, which means you can, for three vectors, you can either get u plus v first, then add the result on w, or getting v and w first and adding the result on u. Either ways, it will give you the same result. Numbers, the probability which is related to the addition closure, the commutativity. So u plus v is equal exactly like v plus u. I want you to remember the operations, how we did it on vectors. Okay, once more, there exists 0 belongs to v such that v plus 0 will equal to 0, which is the existence of a 0 vector. What's the 0 vector? It's the null value, which is simply can be added to any vector and it's not going to change its value. The probability after this is the existence of the symmetry. or the existence of the negation, or the existence of the inverse or the reverse. What I want to say, the existence of the negative value of your vector. So if I have vector 1 and 1, I should have the vector negative 1 and negative 1. If I have the vector 1, 2, 3, I should have the vector negative 1, negative 2, negative 3. Once you add them together, you will get the null vector. Those are the conditions that should be found in order to have an addition closure. A failure in any of these properties, it means it is not a vector space. Also, we have the scalar multiplication. So multiplying A by V, it will equal to V, which means if you multiply the number by the coordinates of a vector, okay, belongs to a vector space or the set of vectors, it should be applicable. A times V is equal to V capital, which is the vector space. Also, the associativity of having two constants A and B times V. So I should be able to multiply A times BV, and it's going to be exactly the same like multiplying AB times V. Also, the distributivity property, which means A can be distributed on two vectors in the following manner, and also the distributivity of scalars on one vector as you saw. Also, the existence of the identity of multiplication. Under all of these conditions, it's going to be a vector space. Okay, within the next slide, let's see some examples on the vector space. And this is really very important, how to see those relations. So if I'm talking about R, which is the set of all real numbers, it represents a vector space. Let's go through the properties one by one. If I have any number on the real number and added two numbers, the real will belong to the set of real numbers. So if I have, for example, 1 and 0 and added on 2 and 0, the result will be 3 and 0. If I have 0 and 0, which is the existence of the origin. If I have 1 and 0, I would have negative 1 and 0. So if I have 1 and 0 and multiply it by 10, it will be 10 and 0. If we multiply it by negative 10, so it's going to be negative 10 and 0. If you have 1 and 1, 1 and 0, and you multiply it by 1, which is the identity, you will have 1 and 0. So R represent a vector space. Also, for the set of R2, which is the two dimensions, real numbers in X and real numbers in Y, which represent the plan. This is also supposed to be a vector space, and it's really very simple and obvious. Any point consists of two components. If you add it on another point, the result will be two components. If you have a point which has two components and multiplied by a number, the first component will be multiplied and the second component will be multiplied, and so R2 represent a vector space. In a similar manner, if I'm talking about R3, which represent the set of X, Y, and Z, the set of the three coordinates, as you can see. So this is X, that's Y, that's Z. Any point or any vector belongs to the three dimension, you will have three components, one representing X, the other representing Y, and the third representing Z. And all the 10 properties are held with you, so 100% it represents a vector space. So R2, which could be written in this way, R2 is the set of X, Y, such that both X and Y belongs to R. Or R3, the set of X, Y, and Z, where X, Y, and Z belongs to R. Also, R5, it's a vector space, and so on, which is a generalization to this concept. But R5, each component in R5 will contain 5 components. So that's the first component, second, third, fourth, and fifth. And all of them are members in the real set. Also, the set of 2 by 3 matrices. The set of 2 by 3 matrices, which means all the 2 by 3 matrices. The set of 2 by 3 matrices, which represents the set of matrices which have 2 rows and 3 columns, where from A up to F, all of them belongs to the set of real numbers or the set of R, also represent a vector space. If you have 2 by 3 matrices and you added them on each other, the result will be a 2 by 3 matrix. If you have a 2 by 3 matrix and you multiply it by a number, the result will be a 2 by 3 matrix also. So it is hold and it is valid for all values perfectly, which is really very good. Okay, for vector space. If we are talking about Rn, which means the set of all numbers from x1 up to xn, such that xi belongs to R, which is a vector space, the set of all matrices with the dimension m of n, blah, 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 it's gonna also represent a vector space, the set of diagonal matrices. If you have a diagonal matrix from a certain dimension, if you add it on a diagonal matrix from the certain dimension, the result will be a diagonal matrix from the same dimension. If you have a diagonal matrix and you multiply by a number, all the elements on the diagonal will be multiplied, so it will lead to the same concept or reserving the same concept. So as we remark, all the 10 requirements can hold for all of these cases or all of these examples. Okay, once more, I want you to remark that V be a vector space. Then, if I told you that V is a vector space, what do you gain from all of this? You will gain the following benefits or the following remarks. First of all, for each vector, its symmetric is unique. So each vector belongs to this vector space, its symmetric, which means the negative of this vector is also belongs to this set of vectors. The existence of the origin. If you have an origin for V or for a vector, it will be the origin for the vector space. The negation, the multiplication of a negative value in a certain vector will result in a vector that belongs to the vector space. Multiplying by a number, similar way, it will be a vector that belongs to the vector space. So it's really very important. Here, one of the exercises that I want you to go through it with me. Let's say V, which is the set of x and y, such that x is greater than or equal to 0 and y is greater than or equal to 0, which represent actually the set of all points belongs to the first quadrant. Okay, with the standard operation, it means this is a vector space. Let's justify our answer. First of all, if you have, I'm sorry, I want to discover if this represents a vector space or not representing a vector space. Let's remember the 10 commitments or the 10 points. You will find some of them are satisfied and others are not satisfied. For example, the addition of any 2 points exists in x and y will result within the first quadrant, will result in a value in the first quadrant. Let's say the point 1 and 1 and the point 1 and 3, if you add them together, you will have a positive point. Okay, if you those are for the positive point. If you have a point 1 and 1 or 1 and 2 and multiply by a positive value, you will have also a point which belongs to the first quadrant. So most of these exist, but I don't think this property exists. Even the existence of a zero already exists in the first quadrant. You have the point 0 and 0, so it's already satisfied. But when you multiply by a negative to get a negation of a certain value, it's not gonna belong to the first quadrant. And a failure of any of these points prevent this set of vectors to represent a vector space. This is written in here. Actually, V is not a vector space. Not every element in V has an additive inverse, which means if you have the point 1 and 1, for example, and multiplied by -1, you will have -1 and -1, and -1 and -1 is the negation of +1 and +1, and it doesn't exist in this guy. Once more, this is a very famous example for the failure of one of the properties, which means V of xy with the condition in x is greater than or equal to 0 and y is greater than or equal to 0. This is not representative for a vector space. Okay, let's look to the set of V where we have x and the half of x. So the y component is half the value of the x component. Does this represent a vector space? Let's justify our answers. Let's think carefully. Let's think carefully about all the 10 commitments as I told you. If I have x plus half of x and add it on y plus half of y, the result will be okay. A second property already exists. It is already commutative. So x plus half of x and y plus half of y, you can replace them. Okay, the multiplication, the existence of a zero. If x is equal to 0, then you will have 0 and 0, which represent the origin. The existence of the negation of the, or the inverse of additive of the addition, which is negative x and negative half of x. Also, if you multiply it by scalar, you will have the same results, all of them. Let's check them one by one. Yes, V is a vector space. We check all the properties in one by one. As I told you, this is the vector. Okay, if I add it on y plus half of y, this is the result that I have, which is a proof that it is already exist. Clearly, addition is closed under addition. Clearly, addition is associative, so I can replace them. Also, the element 0 and 0 exist, as I told you. The negation already exists. The multiplication by scalar also exists. So V is closed under scalar multiplication. And so the distributivity, everything. So this is a vector space. So the set of all vectors with x is equal to half of x, or the y component is simply half the x component, simply it represents a vector space, as you can see. Now I will go to the vector subspaces. For a vector subspace, which is a set, a part of a vector space. So we already have now an imagination of what we mean about a vector space. I usually look to a vector space to a circle with this dimension. The sub-vector spaces are smaller circles inside the big one. The only conditions for a sub-vector space is to have the following. Number one, the existence of the origin. So the origin of the vector space should belong to both of them, the vector space and the sub-vector space. Number two, the addition closure, H, U, and V, you add them together, the result will also belongs to the set of all vectors. The multiplication by a number, if you have a scalar value and multiply it by a vector, the result will also be a vector that belongs to the vector space. So it's really very simple. Let V be a vector space and W is a subset of V. W is said to be a vector subspace of VF. Those conditions can hold. Remark that every vector space V is a vector space. Every subvector space of vector space V is a subvector space. So each unit as a subset of a bigger unit by itself, it's a vector space. And every vector space is a vector subspace from itself. Okay, how can we verify that a vector to be a subspace of another vector space? The following conditions must satisfy. So let's check, for example, if I have V, which is the set of all values of A and 0 such that A belongs to R. Is this a subset of R2? It has two components, and I'm talking about R2, which is the set of all vectors with two components. So this guy, which represents the elements of an x-axis, does it represent a subvector space from R2? I believe so. Why? First of all, the origin of this guy, when A equal to 0, which is a value belongs to R, you will have the origin 0 and 0. And the origin 0 and 0, it's exactly like the origin in R2. So, fact number one is correct. 0 and 0 belongs to V. Number two, if I have A and 0 and B and 0 and you added them together, the result also will belong to the set of a 2 by 2 vectors, which is A plus B and 0 belongs to V. Number three, if I have A and B, I'm sorry, A and 0, and multiply the components by any constant value or any scalar, the result also will be on the same shape. So yes, A and 0 for A, such that A belongs to R, represent a subvector space from R2. This is really a very good example. يبقى V is a subvector space of R2. Okay, let's see further examples. Let W be the set of all points on any given line Y belongs to M and X. M and X represent a subvector space from R2. Okay, the origin in the plan already belongs to this straight line, and any point belongs to the line Y equal M of X will be a coordinates that belongs to the W or this set, which has the addition closure and the multiplication by scalar closure. The vector subspace, these also are called vector subspaces. R3 from R3, it's a vector subspace. So any vector space, it's also considered a subvector space from it. The set of the origin, just only the origin by itself, it represents a subvector space from any vector space. So this should represent a subvector space from R3. For every R3 passing through the origin, every R3 components or line belongs to R3 but passing through the origin, it also represents, it's a non-null and also represent a subvector space from R3. Also, the set of plans, which is K1 V1 plus K2 V2, where K1 and K2 are non-collinear values. I'm sorry, K1 and K2 belongs to R, and the vectors are non-collinear, which represent the set of the plans passing through the origin. It also represents a subvector space from R3. Let's check if this set of A and A plus 1 represent a subvector space from R2. Let's check all the following, or at least the three operations: the zero existence, okay, the addition closure, and the multiplication by scalar. If you try to think about this, if I have A and A plus 1 and added on B plus B plus 1, the result will be A plus B for first component, while the second component is going to be A plus B plus 2, which is not on this shape or in this form of your vector space, and that's a Villiers enclosure, so it doesn't exist. If you have A and A plus 1 and you multiply it by 2, the result will be 2A. This is going to be 2A plus 2, not 2A plus 1, which is a failure in the form of this vector shape. So no, it doesn't represent a subvector space. I will add one more reason. If A is equal to 0, the origin will be 0 and 1, not 0 and 0, which is the origin of R2. And for subvector space, or for vector space to belong to a certain vector space, they should share the origin. I will stop at this part for this week, and I will continue next week, inshallah. Please try to go through all of this, and I will try to send you as fast as possible the Lisbon slides as soon as they reach me. Thank you very much. And as I told you, keep up the good work. Please try to review all your slides. Go through them one by one. If you have any questions, please try to either write them in the comments beneath the vids or send them to me on the WhatsApp. It would be my pleasure to answer it at any time. Thank you very much for turning in, and thank you very much for listening to this video. With my pleasure, and I wish you all the best. Thank you very much. Thank you. Bye bye.